Okay, and here's the other thing we're going to do in terms of changing the appearance of radicals. We are going to, once again, work on rationalizing denominators. And just like with simplifying or extracting roots, the idea here would be we don't want a radical in the denominator. To get rid of it, we're going to use inverses. So if it's a square root, we're going to try and get it to be squared. If it's a cube root, we're going to try and get it to be cubed. But we have a limited number of options for how to do that. You can't just go in, so let's look at this 3 over root 5. You can square that and say, okay, I've got 9/5. That's great, but that's not equal to the number you started with. That's not the same as 3 over root 5. So we want to figure out how to get rid of the radical in the bottom without actually changing the value of the fraction. So we're instead going to be looking at, can we add 0 or multiply by 1? And in this case, the answer is yes. If we're careful about it, we can multiply by 1 in a way that'll make these things simplify really nicely. I feel like this typing looks really little. So for 3 over root 5, we've already done these, but again, I wanted to start here because it's the exact same idea with the other ones. If I want to make the denominator into root 5 squared, I'm just going to multiply by another root 5. If I don't want to change the value of the fraction, I'm going to do it to the top as well. So I'm going to get 3 root 5 over root 5 squared. Or you can write it, it doesn't matter which way. You could write it like this if you like that as well. Either way, what we should get is 3 root 5 over 5. So just like that, we want to tackle things like 6 over the square root of 2w. If I don't want a square root in the denominator, I need to figure out how to get it to be squared. Squaring's a nice easy one because to get something to be squared, you just multiply it by itself. I feel like I'm writing too tiny, 2w. Okay. If we don't want to change the value of the fraction, whatever we do to the bottom, we have to do to the top. So really, we've just taken 6 over root 2w and multiplied it by 1. So I know it has the same value that I started with. On the top, I have 6 root 2w. On the bottom, I have root 2w squared, which means I have 6 over root 2w over 2w. Again, you're not going to get 4w squared. The square root and the square are inverse operations. They're happening back to back in my order of operations. So we should just end up with the 2w. The square strips off the square root. I can go one more step in this one, so watch for simplification. Here I have 6 is 3 times 2, and I can cancel a 2. So really I end up with 3 root 2w over w. And that is a fully simplified answer. All right, let's move down to row 2. Getting just a little bit messier as we go. For this one, this is an interesting one. There's a couple of things you can do. One of them saves you from having an extra step at the end. So what a lot of people will do is multiply top and bottom by 3 root x, and that will work. That's totally fine, but there's actually a slightly quicker way to do it. You'll end up having to cancel at the end if you do that. Actually, I think I'll have to cancel here, but you'll have even more to cancel at the end if you do that. Really, I don't need the 3 to be squared. I just need the root x to be squared. So it's enough to just multiply by root x over root x. So again, if you're curious, work it through with the multiplying by 3 root x. There's a lot of things you can do that are perfectly right and will get you to the right place, but maybe get one extra step in the mix or aren't quite as efficient. That doesn't mean that it's bad if you do those. I just wanted to point out that you can skip a little bit there. So I get x root x on the top, and I get 3 root x squared on the bottom, which means I have x root x over 3x. And like I said, I actually do get to cancel in this one. This is a big quotient. Those x's are both factors, so multiplication, division are inverse operations. We can cancel, and I just have root x over 3. So it simplifies really nicely. Okay, last of these ones that just have one thing floating around in the denominator, sort of last. The next one's a little bit different. If I have a 3 times 4th root of k, I'm sorry, divided by 4th root of k, this gets a little trickier. Squaring is not the inverse of a 4th root, so if I just multiply by 4th root of k, I'll have 4th root of k squared, and that doesn't get rid of the root for me. What I really want is to multiply by the 4th root of k, that's supposed to be a 4, 3 times, so that I end up with a total of 4 of them. If I'm going to do it to the top, to the bottom, I better do it to the top. So I end up with 3 times the 4th root of k cubed. You don't have to have the parentheses, but it just seemed like it looked a little cleaner to me. On the bottom, if you have the 4th root of k cubed and you multiply in another 4th root of k, that means you're multiplying together a total of 4 of them. That's 4th root of k to the 4th. So think about inverses. Squaring and square rooting are inverses. Squaring and 4th rooting are not inverses, but 4th powers and 4th rooting are inverses. So now on the bottom, I just have k. If I take the 4th root and then raise to the 4th power, those operations completely cancel each other out, and I just end up with the number I started with. On the top, you can leave it as is. I kind of like the way it looks better if we move that cube. Oh, hold on, that's a 4th root. If we move that 3rd power, that cube, in under the square root, it just seems a little less messy, but they're equivalent statements, so you don't have to do that if you don't want to. Oh, and a fraction bar kind of looks nice. Okay, so remember, if you have cube roots or 4th roots or anything like that, higher roots, you can't just multiply by the same thing once. That doesn't cancel out a higher root. All right, so cube root of 2y over 7. So this is changing the appearance of radical expressions, and this is a radical expression. We have the root of a fraction. And in general, when we talk about simplifying radicals, one of the things we mean is make the number under the root as small as possible, and another thing we mean is we don't want radicals on denominators. And sometimes people think they can get away with it in this case, but really we do have a radical on the denominator. That 7 is part of the cube root as well. So if I can cancel anything under the square root, I would, the cube root, but I can't. So I'm going to use that same property I used when I was extracting, only the quotient version. It really is the same thing though. Radicals split really nicely over multiplication or division. So I'm going to take advantage of that division fact right here. Okay, so really all I need to do to simplify this is deal with the cube root in the bottom. So just like in the last example, multiplying by the cube root of 7 doesn't really do the trick. You get the cube root of 7 squared, cube rooting and squaring, not inverses. What I need is a cube root of 7 to the 3rd, so I need to multiply that single cube root I have by 2 more. Whatever I do to the bottom, I'm going to do to the top so that I'm not changing the value of this fraction. So on the top, I've got the cube root of 2y, and I'm going to go ahead and do what I did last time and move that square underneath. So that becomes 7 squared, which again, you can skip some of the steps I'm doing. If you're not sure how many, you can ask me, but if you want to go straight to writing 49 there, totally fine with me. On the bottom, oh no, I have my batteries getting low. Cube root of 7 cubed. I multiplied a single cube root by 2 more. That's a cube root cubed, which cancels. So in the top, I'm going to go ahead and write 49 here because I'm running out of horizontal room. The last thing I would do there is say, since that's a cube root times a cube root, there's no reason to write it twice. You can just mush it together. The same way we can take roots apart across multiplication, we can squish them together across multiplication. So I have 49 times 2y, which is a 98y over 7. And that would be considered a simpler answer than what we started with. Okay, I'm going to do one more, and then I'm going to pause and plug in, and I'll come back and do the rest. So this is a really similar idea. The problem is the radical really does apply to the denominator. But before I go splitting roots up in this case, I think you should check and see if you can simplify what's underneath the root. And this really simplifies a lot. I can divide 150 by 3, and that'll leave me with 50. I can divide x to the 7 by x cubed. There's 7 factors of x on the top and 3 on the bottom. So if I cancel, that'll leave me 4 factors of x on the top. And similarly with the y's, there's 4 y's on the top and 7 on the bottom. So if I start canceling, it'll leave me 3 y's on the bottom. So I have a 50 x to the 4th over y cubed under a square root. Okay, so now I'm going to go ahead and split it up. 50 x to the 4th. And actually, there's more things I can do as well. Lots of things I can do. Over the square root of y cubed. So in whatever order you like, you need to rationalize the denominator and you need to extract roots. I'm kind of tempted to extract roots first, just thinking it might make the rationalizing easier, but it really is your choice. So I'm going to go ahead on the top and say 50 is 25 times 2. And x to the 4th is already a perfect square, so I like it. On the bottom, I have y squared times y. So splitting that up, I have root 25, and I'm going to move that root x to the 4th out in front. I usually do that in the last step. And then I'm going to leave that root 2 alone because I can't do anything with it. On the bottom, I'm going to separate the y squared and the y. So taking the square roots, square root of 25 is 5. Square root of x to the 4th is x squared. The root 2 is stuck. On the bottom, square root of y squared is y. Root y is stuck. Okay, so final step, and again, you can rearrange order here. This is a nice thing when you're working with radicals and products and quotients, or exponents and products and quotients. You have a lot of flexibility on your order. So I'm going to multiply top and bottom by root y. So my final top is going to be, maybe I shouldn't say final. Yep, I'm pretty sure it is final. 5x squared times root 2y. And my denominator, this is going to give me root y squared, which is y. So I have the y that was sitting out in front multiplied by the y I get from the roots. I'm running out of room, so I'm talking you through those steps right there, which is a y squared. And that is a great final answer. No radicals on the denominator, no denominators within radicals. So fractions in radicals is the same kind of problem as radicals under fractions. And we've extracted all roots. Okay, thanks for watching. I'll do a separate video to do the multiply by the conjugate stuff.